Hello, everyone. Welcome. My name is Chris Naroth. I'm a software engineer at Hortonworks, and I'm an Apache Hadoop committer. Primarily, I work on Hdfs, and the title of this talk is Interactive Hadoop via Flash and Memory. I'm planning on covering a few new features recently added to Hdfs to help better utilize cluster resources, specifically getting into some more unique storage media compared to traditional spinning disk. Initially, Hdfs focused very, very specifically on the needs of batch Mapreduce processing. This meant long forward scans over data stored on traditional spinning disks. Over time, though, what we've seen is that there are additional usage patterns evolving. We've started to see that not every Hdfs file involved in batch processing is huge and ideally read from disk. Something smaller, like a Hive dimension table, could be small enough to be held resident in RAM for the duration of a query or even multiple queries using the same input data set. HBase and other specialized applications use more of a random access pattern. And this has led to questions around how Hdfs utilizes cluster resources other than traditional spinning disks. I'm going to discuss two new features specifically, centralized cache management and heterogeneous storage. And these features were driven by the use cases I mentioned for getting better cluster utilization. Before I go further, I also want to thank Arpit Agarwal, my teammate at Hortonworks and fellow Apache committer. Arpit crafted all of the content that you'll see today related to heterogeneous storage. Unfortunately, he couldn't make it here today to join me for the actual talk, but I definitely want to thank him for his contributions to this talk. To set up a framework for discussing the new features, the first thing I want to do is just recap exactly what happens at a high level when an Hdfs file read happens. This sequence diagram shows you at a high level what happens when an application opens an Hdfs file and starts reading bytes. This is a distributed interaction, so I've overlaid the sequence diagram with gray boxes to indicate the machine boundaries. First, the DFS client contacts the name node and makes an RPC call to get the block locations for a particular named file. The response from the name node is a list of block locations. This is a list of every data node that currently holds a replica of that block. The DFS client selects one of those data nodes and then issues a read block RPC call to that data node. The data node handles this by opening the underlying block file stored on a local file system, reading the bytes, and writing them back on the DFS client's socket connection. The DFS client receives these bytes, and here's where the application can do whatever application-specific processing makes sense on those bytes of data. That's the basic interaction, and for a multi-block file, this set of interactions would be repeated multiple times. The next thing I want to show is a slight variation on this. We call this short circuit reads. A short circuit read is possible when the DFS client process and the data node process happen to be co-located on the same physical node in the cluster. So this is, for example, a map task that is achieving ideal locality. It's running right on the same machine as the physical block file. Short circuit reads, just so it's absolutely clear, anytime we say short circuit reads, it's something that is by definition impossible in the remote read case. During a short circuit read, the DFS client bypasses the step of transferring bytes through a TCP connection through the data node process. Instead, you'll see that step 2 here has been replaced with a different RPC call, request short circuit FDs or request short circuit file descriptors. And what's happening in this interaction is the data node process opens the block file, obtains the open file descriptor, and then transfers it to the DFS client via a Unix domain socket. And from there, step 3 shows that the DFS client process can read directly from that file descriptor, and this saves the overhead of transferring all of the bytes via TCP through the data node process. Now, so far, in none of these slides have I mentioned anything about RAM. So we can ask ourselves the question, exactly where does RAM fit into this picture? Hdfs itself is not necessarily doing anything specific to manage its RAM, so the answer becomes here. It's all managed at the OS layer in the form of the buffer cache. The OS is using any unused RAM on the box to buffer the block file data that is stored in the local file system. So in some sense, Hdfs is already utilizing RAM, and we're getting it automatically from the OS. So great. What's the problem, though? The problem turns out to be that purely relying on the OS buffer cache does have some shortcomings. First, we lack control. The kernel decides what to retain in cache and what to evict based on its observations of usage patterns on files. And in this case, what I'm talking about is the raw underlying Hdfs block files, not the logical Hdfs file that you interact with. Now, there is a lot of very, very clever work inside the Linux kernel to make sure that the OS buffer cache does a good job. But in some cases, there's simply no way for the kernel to know with certainty what our intentions are in terms of access pattern. Whether we intend to read the same file repeatedly or just scan it once and then never need it again. Second, this can lead to suboptimal utilization of RAM. For example, execution of Mapreduce tasks for multiple jobs can get interleaved on the same host. The activity of one job's task could trigger eviction of data that would have been valuable to retain in cache for the other job's tasks. Earlier, I mentioned the use case of a Hive dimension table. This could mean that hundreds or thousands of map tasks in a Hive query need to read the same file, but when interleaved with some other job's tasks, it's quite possible that the kernel would choose to evict the pages of that dimension table in favor of something that it thinks would help the other job. So to address this, Hdfs has a new feature called Centralized Cache Management. First, it provides users with explicit control of which Hdfs file paths to keep resident in memory. Later, I'll show an example of exactly how to do this, what it looks like in terms of user interaction, and we'll take a peek behind the scenes, too, at what happens when you request caching for a path. Second, centralized cache management allows clients to query for the block locations that hold a replica cached in memory. So the benefit of this is that it opens up the possibility of scheduling improvements in the future. For example, the Mapreduce scheduler could potentially choose to favor placing map tasks on nodes where the replica is already present in cache, as opposed to only local on physical disk, but not necessarily resident in RAM yet. This part isn't actually done yet, but the Hdfs APIs are in place such that it could be enabled as a future enhancement. Third, something I want to mention as a side benefit is that the implementation of centralized cache management utilizes off-heap memory. And the benefit of this is that you're not going to need to suddenly grow the data node process JVM heap size to fit entire large sets of block files, and then because of that incur the shortcomings of large Java heaps. You won't need to deal with large garbage collection passes and fiddling knobs on the garbage collector to optimize for that. Before you can make use of centralized cache management, there are a couple of prerequisites. First, the native Hadoop library must be deployed. This is because there is a lot of tight underlying integration with the OS for some specific system calls. So libhadoop.so must be deployed. This is currently implemented on Linux only and not Windows. Please excuse me while I take a sip of water. I think a port to Windows would be a very trivial thing at this point. I think this would be a matter of swapping out 2 system calls that are currently Linux-specific for the Windows equivalents. It's just not done yet, but patch is welcome. So if you're a Windows user and you want to contribute to Hadoop, that would be awesome. The next prerequisite I want to mention is that you'll need to set the process U limit for maximum locked memory. The default for this in typical Linux distros is pretty small, certainly too small for what we're talking about here, which is we're going to be locking entire block files into RAM. 128 megabyte block size is pretty typical. And the configuration for this is somewhat specific to different distros. On the Ubuntu machines I used for testing, this required editing etc security limits.conf. Also in Hdfs site.xml, there's a bit of configuration you'll need to do. There's a new configuration property, DFS data node max locked memory. This defines how much RAM you're willing to commit to cached blocks. And in most typical deployments, this will probably line up with what you chose for the U limit. There are a few new concepts to understand, and I put this slide together and then I realized it's actually more intuitive to explain them in the opposite order. So I'll start with the cache directive. A cache directive specifies a file system path to cache. Specifying a directory caches all the files in that directory. It's not a recursive operation, but it will go one level deep. So this is well targeted at the use case of a Hive table, where you think about introducing a new partition would involve introducing a new file under that table's directory. By putting a cache directive on the directory, you can say that any new partitions introduced, you want to have them cached automatically. You can optionally specify a number of replicas to cache. So thinking of a typical configuration where you're replicating 3-way, you may decide that you want only one replica to be cached in RAM. You may decide that you want all 3, so you're guaranteed to get a cached copy no matter where your task gets placed, as long as it's a local read. You can also specify time to live, so that your cache directive will expire after, say, an hour automatically, at which point that data would be uncached. There are a couple ways in which a cache directive is not quite the same as a Hdfs path. So, for example, if you add a cache directive on a path that does not exist, that's actually okay. You won't get any kind of file not found error like you would normally get with an Hdfs operation. The cache directive is not really a file. It's a request to do something about a file. So what happens is we will still accept that cache directive, and if at some point that file comes into existence, it's automatically eligible for caching at that point. The other new concept here is the cache pool. And every cache directive must be associated with a cache pool. A cache pool is an entity for administration purposes. And what you can do is control quotas with this. It has permissions. It defines a maximum number of bytes that can be cached across all directives within that pool. Before anyone can create cache directives, there must, by definition, be a pool, because every cache directive must live inside one pool. This sequence diagram shows a high-level process flow of what it looks like to use centralized cache management. First, an administrator creates a cache pool. Only an administrator can create a cache pool, and specifically what I mean by that is that it has to be done by the Hdfs super user or someone who is a member of the configured super group. After that, and the intention behind that is that RAM is a scarce resource, much more so than disk space in a cluster. So this is intended to guarantee that a cluster administrator has considered the impact of using centralized cache management before exposing it to users. It's offering administrators some control over that. Step 2, users will create their cache directives based on what they want to cache. Third, the Hdfs cluster arranges to cache those blocks. That's super hand-wavy right now, of course. But we'll get more into specifically what happens in that step 3 in a couple slides later. And finally, once that data is cached, the users can submit whatever their workloads are, such as Hive queries or traditional Mapreduce jobs, and the block data would be read from cache instead of a longer latency read from disk. Okay. In the next several slides, I'm going to show what it looks like to actually use centralized cache management. And for most users, this would mean using a set of new commands that are provided on the Hdfs CLI. Here we see that first step of an administrator adding a pool named common pool. And that is followed by listing all the pools that are currently configured in the system. The pool name is the only required field. We could have specified permissions, a limit to the amount of cache bytes in the pool, and a maximum time to live for cache directives inside that pool. But we didn't bother, so it gave us the defaults, which are 755 for the permissions. The permissions are very, very similar to Unix file system permissions, so that's why you see the notation there. Read permission means that you get to see what cache directives are defined there. Write permission means that you get to create new cache directives in there. Execute is currently unused. We're seeing 755 here just because that's a consistent default. Okay, moving ahead. Next, we see a user adding a cache directive. And to do that, the user specifies a path that they want to cache. Here we've cached the path hello Amsterdam, and we've added it into the pool that we defined in the prior slide, common pool. We then ran the list directives command to see that our cache directive was in fact in place there. Once again, I just stuck to the simplest form of the command here and accepted defaults. I could have specified a replication. Default replication is 1. I could have specified a time to live. That defaults to unlimited. Okay. At this point, we're seeing that the user is done with caching a particular path. So now we can remove that cache directive. Listing directives this time shows that there are none left. One thing I want to mention here at this point is that the actual uncaching of files is not happening synchronous with this command. We'll see later that for both caching and uncaching, there are a series of asynchronous handoffs involved. So we'll get more into detail about that later. And in addition to the new CLI command shown here, all of those CLI commands are implemented in terms of new APIs that we've defined on distributed file system. Those methods are accessible, so if you had custom application needs that were different from what we've provided on the CLI, that's possible as well. Okay. At this point, we'll take a closer look at what happens behind the scenes when you start caching, when you start issuing cache directives. I'll take one more sip of water. Please excuse me, battling a cold. All right. The entire process, end-to-end, involves a series of asynchronous handoffs, like I mentioned. So I wanted to provide one slide that attempted to put all of those interactions together so you could see end-to-end what happens. The first step is that the user adds the cache directive. And this is an interaction between the client and the name node only. The name node handles this by persisting the new cache directive to its edit log, and eventually that also makes its way into the FS image during the next metadata checkpoint. So what this means is that cache directives are persistent. If you need to restart the name node, you don't then need to turn around and immediately restore the cache directives that you had put in place beforehand. The second interaction shown is initiated from each data node to the name node. Periodically, the data node will send a cache report to the name node. The cache report is a full list of all the block replicas that are currently cached in memory by this data node. The name node uses this information to decide how to schedule caching or uncaching work as needed at each of the data nodes. The third interaction is the classic data node heartbeat to the name node. However, what's been changed is that we've enhanced that protocol so that the name node may reply with commands asking the data node to either cache or uncache blocks in response to the upstream cache directive requests from the users. The fourth and final interaction is between the data node and the local file system, and this is the point where the action really happens, because what happens here is that the data node uses the mmap system call to memory map the block file into its process, and also the mlock system call to pin the pages of that block file into RAM and thus prevent them from getting page swapped out. We can use the pmap utility to inspect the address space of the process. And what I've shown here is the details of a data node process that has cached the two block files of the Hello Amsterdam file that was mentioned in the prior commands. This is an Hdfs file with two blocks, block size 128 megabytes. We can see that these are both memory mapped into the data node process. And what this tells us is that the mmap system call worked. In this slide, I'm running vmtouch to get a report on each of the underlying block files. And the important thing to note here is that for both block files, it's reporting resident pages are 100% resident. So this tells us that mlock worked. We're going to be, all of the pages of that file were brought resident into memory, and we're going to keep them in memory. They're not going to get swapped out. So any read of either of these block files will be satisfied from cache instead of requiring a read from disk. I also want to briefly mention zero-copy reads. This is a further enhancement on top of centralized cache management. And what this will allow applications to do is read straight from direct byte buffers backed by the memory-mapped block file in the data node process. And this eliminates some overhead involved in copying bytes read from the block file into intermediate buffers in the application layer before they can actually be processed. Additionally, what we can do is skip the work of checksumming because we verify checksums at time of mmap and mlock. So at this point, it would be redundant to verify the checksum over and over again. In order to take advantage of zero-copy reads, it would require application code changes. There's a new read API. The reason for that is the existing read APIs are very, very much wedded to the notion of byte arrays living in user space. So there was, unfortunately, really no way to simply drop this in. So you would have to use a new API to take advantage of this. At this point, I'm going to transition away from centralized cache management and into discussing another new feature, heterogeneous storage. And I'll be happy to address questions about either feature at the end of the talk. And once again, I also want to thank Arpit Agarwal for providing the content in these slides. So similar to centralized cache management, the high-level goal of heterogeneous storage is to provide users with ways to better utilize the resources in their Hdfs clusters. We want to extend Hdfs to better support a variety of storage media, not just traditional spinning disks. And we actually heard Arun Murthy touch on this in this morning's keynote. We want to give end users the control they need to decide which pieces of data get stored on which media, because ultimately users have more knowledge of the specific needs of their own applications running on top of HDFS. Compatibility is always a concern as well, so we sought to reuse existing APIs as much as possible in a backwards compatible way. This slide shows the specific kinds of storage media that we were really targeting with this feature. And this is after a lot of discussion of proposed use cases and what we're hearing users want to be able to do with their clusters. We chose to focus on traditional spinning disks, solid-state disks, and RAM as a storage layer. The thing I find interesting about this table is that what we can see is that storage is not one size fits all. Each type of storage has a different cost factor and also a different set of use cases that it best satisfies. So for example, we see that spinning disk is very cost effective for large volumes of batch processing, but random access is much less efficient. The faster random access time of SSD seems to fit well for HBase, but it may not be the best fit for batch processing. And interestingly also, RAM can be thought of as a kind of very fast, very expensive, in relation to the others, storage, with, of course, the huge limitation that it's actually volatile and not persistent. But this could be a great fit for temporary data sets, something like a materialized view in Hive that only really needs to survive temporarily during the execution of a query or a set of related queries. This is conceptually similar. You could think of it as similar to RAMFS or TempFS on Linux. And the last row of this table is question marks, because we also wanted to remain open to the possibility of entirely new kinds of storage media that we haven't even seen yet. That meant that our engineering efforts needed to consider the possibility of future protocol enhancements and make sure that those protocol changes could be made in a backwards compatible way to support those media. Much of the work that has been done on heterogeneous storage to date has been foundational in nature, and this picture shows what the Hdfs storage architecture looked like before work began on heterogeneous storage. The data node logically aggregated multiple local file systems sitting on top of multiple physical devices. This essentially meant that each data node presented a single unified logical unit of storage. The storage reports and the block reports sent from the data node to the name node periodically, these reports contained no distinction between the multiple physical volumes attached to that data node. So when clients would write data, they would write to that unified logical unit of storage. They had no way of determining which physical device the write would land on. And you can see this architectural choice all the way down to the configurations in HDFS site XML, where you set DFS data node datadir to this comma-separated list, which are your various mount points on your underlying local file system. This slide shows how the storage architecture has changed with heterogeneous storage. Now we see that the data node is capable of maintaining a distinction between the different storage types that could be attached to it, whether that means spinning disks, SSD, or RAM. The storage reports and block reports sent to the name node are now grouped by storage type or storage device. So the name node has awareness of how much of each particular resource is available at each data node. And this enables block placement decisions based on the desired media type. Finally, we provide API enhancements so that the clients can choose to place their data on specific storage types. Let's talk a bit more about how clients request a specific storage type. The API enhancements that I mentioned allow the application to pass an optional storage hint to HDFS at write time. This specifies the application's preferred storage type. Note that this is advisory. So if that specific storage type doesn't have sufficient capacity to satisfy the request, then we fall back to spinning disk. And this is actually a point that has been debated quite a bit during design discussions. Another possibility would be to fail fast if the specific storage type requested isn't available. Ultimately, we felt it was safer as a default to make sure the data gets written somewhere. And we'll see later that there is a possibility of asynchronous migration to the desired storage type if capacity frees up later. This is something that still goes back and forth, and it could become a configurable behavior later in future releases. I already touched on this briefly. There are two separate write use cases that we intended to support. One is specifying the preference at file creation time, and the other is changing the preference on an existing file. If specified at file creation time, then replicas are written directly and immediately to the desired storage type. If changing storage preference on an existing file, then this involves triggering a migration of existing replicas from one storage type to another in the background. Quota management is definitely a concern, especially when you consider the content from a few slides back showing order of magnitude difference in cost for different storage types. SSD will be much more expensive and therefore more scarce than spinning disk. And we're building extensions into the existing quota mechanisms so that administrators have the tools they need to specify quotas per storage type instead of just globally. This slide shows a sequence diagram of file creation with consideration of storage types. First, we see an administrator configures storage types. This is an action that happens on the data node. Earlier, I mentioned the existing DFS data node datadir property that if you've deployed Hadoop, you're familiar with. This currently lists the local file system paths to be used for storing block files. And this configuration format has been enhanced so that you're able to prepend an optional storage type in front of that path, which is going to be one of your mount points on the underlying local file system. In step 2, we see that this causes the data node to start reporting its separate attached storages to the name node instead of presenting just a single unified logical unit of storage. Step 3, this is happening kind of on the side. It shows the administrator configuring quotas. And then steps 4, 5, and 6 show a variation of the data write sequence that we showed at the start of this talk. The differences now are that the client's requests include the storage preference. The name node responds with block locations that match that storage preference, and the eventual write to the data node writes to the specific storage type. This slide shows movement of existing replicas after changing their storage type. First, we see a user changing file storage type from HDD to SSD. Second, we see the name node scheduling the necessary block migration work to execute asynchronously. In steps 3, 4, and 5, we see the name node coordinating with multiple data nodes to execute block migration from HDD on data node 1 to SSD on data node 2. And finally, this information is reflected in the block location information returned in response to user requests. Earlier, I mentioned RAM as a potential storage type, and this is a feature that is in progress. To expand on this a little bit, we're planning on supporting transient files built on top of heterogeneous storage with RAM as the backing storage type. File writes will go directly to RAM. Earlier, I mentioned RAM-FS and temp-FS on Linux, and you can see how that's kind of analogous to what I'm talking about here. Similar to short-circuit reads, which I mentioned earlier in the talk, we're also planning on implementing short-circuit writes so that local in-memory block replicas can skip the overhead of passing bytes through the data node TCP server. If you decide this data needs to be persistent, then it would be possible to do a form of checkpointing by changing the file storage type and thus moving it back to hard disk. Or you can always just let it be discarded if the data is truly transient. And we think this could be a big win for implementing materialized views in Hive. Materialized views being a filtered or transformed result set based on source data that may be then reused multiple times in a job flow. For further references on either centralized cache management or heterogeneous storage, you can refer to these Apache JIRAs. You'll find design documents and test plans and valuable community discussion on all of those issues. Also, ARPIT has published a great article on the Hortonworks blog giving a high-level summary of heterogeneous storage. And thank you for your time, everyone. I'm excited about these new features. I think it's an exciting time for storage. And the next thing I'm excited to see is what kinds of reference architectures could emerge using these new features as building blocks. If you found this interesting, then I'd also like to recommend a few other sessions for you that are happening tomorrow. Tomorrow at 11:50 is in-memory caching in Hdfs. That's an entire session dedicated to centralized cache management. So if you want a deeper dive on that, you can go to that. And also tomorrow at 1:30 is Big Data Trends and Hdfs Evolution. And this is an opportunity to hear more about how Hdfs architecture is evolving to try to take advantage of new storage media. Thanks again, everyone. And at this point, I want to open it up for Q&A. Okay. So just to repeat the question for the benefit of film, the question is, what if multiple users have requested caching and there's insufficient RAM capacity to satisfy all those requests? The answer is the name node and data node will coordinate to try to cache as much as possible. It's ultimately non-deterministic which ones are going to win and lose in that kind of scenario, but it will try to keep retrying caching all the requested files. So then later, if at some point capacity frees up, you'll find that the file that wasn't getting cached earlier because it didn't have capacity is now getting cached.
Right, thanks, nice talk.
Oh, thank you.
Question about the block size of the Hdfs, which is quite large relative to the amount of data memory available on data nodes, and also the latency with which your cache request comes down, because it's only with every heartbeat you're setting down a cache for a cache set. Did you consider using an RPC to reduce that latency, and what about block sizes? You tend to using larger block sizes to reduce the utility of this.
Could you repeat the last part?
Yes, there's a trend towards using larger block sizes for larger clusters, and that reduces the utility of caching. So, are there any guides you can give us about why you chose this approach? Why you use RPCs?
When you say RPCs,
Well, I mean, the name node it takes 3 seconds or whatever for a heartbeat. So
yeah.
when you want the caching instruction, there's going to be a delay between the name node and the caching instruction down to the data node.
Yeah. What I'm wondering is if you're suggesting, as an alternative, a synchronous interaction from the client. Is that it?
Well, I mean, it's just basically that when a client requests to read something into memory file, it'll send a command to the name node, and then the command to cache that file into memory will take, the delay of the heartbeat being returned, and that could be 3 seconds is a long time.
Yes, yes. I think what that comes down to, so the answer is that hasn't necessarily been considered. I think the reason for it is that the targeted use case was very specifically on files that benefit from being retained for long periods of time. That was the primary use case. So it was seen as something that somebody would start caching, well before any jobs consuming that input data would launch. It doesn't mean that what you're describing is an invalid use case, though, at all. So what could potentially happen there is programmatically adding a cache directive, and then a bit of a loop querying the block locations. The block location information now describes which block locations are cached. You could potentially loop a bit, wait for caching somewhere. Pardon me? Yes. 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 But that's a good question. Thank you.
What release is the Heterogeneous? Is it ready to go?
No. So there's Apache Release 2.4.0, which has a release candidate right now. And this is foundational groundwork. I talked about in the slides there was traditionally the data node simply presenting a single logical unit of storage. And the phase 1 of heterogeneous storage had to split that apart. And that's what's done. Phase 2, which is in development right now, is the APIs that will actually allow you to specify storage preferences. So at this point, there's not a release I can point you to that has the full feature baked end to end. I'm afraid I'm not familiar enough with Spark to answer your question. Do you have some familiarity with Spark?
No.
Okay. I wonder if anyone in the audience does have, yes?
Yeah, I think this is kind of a basically for a pilot to be sharp of the Spark. We want to get the data in there, so give the presentation on it. So I don't this doesn't really answer your question. Spark is good in front of the application in the program.
Maybe if people are interested in talking about that more, this would probably be very educational for me, too, if anyone wants to chat afterwards. Anything else? Yeah. No, we haven't gone that far with this. So the question is around benchmarking of the zero copy reads, specifically with. Could you repeat for me the hardware enhancements you were interested in?
Yeah, so there's networking hardware that is basically supporting all the data abstractions we're looking for in
Okay.
Memory communication between multiple nodes, so no CPU, etc.
Okay. Yeah, we don't have that. The benchmarks around that we've done so far are interesting. I don't have a slide to present around that, unfortunately. What we've seen so far is that in terms of a raw read benchmark, so just the DFS client in a very tight loop reading bytes, we have seen up to a 5x improvement on making the jump from the traditional read API all the way to a fully cached file with the zero copy read API, up to 5x improvement. But then getting into more realistic workloads where there's actually some amount of processing that you're doing on those bytes, the impact gets much less than that. We certainly do see some impact, but I'm almost uncomfortable presenting anything because it's not finalized yet, I feel like we don't have a finalized benchmark we can present. And certainly nothing that is using specialized hardware like you asked. Yes? The question is, how do we decide which one to cache? And so I mentioned the cache reports coming in describing which blocks are cached on a particular data node. That information goes to the name node, and the name node uses that information to make decisions. So basically what that allows the name node to do is try to cache where there is the most available RAM to do so. Failing that, say you're starting completely from scratch and nothing is cached yet, and there's the same amount of RAM available everywhere. I actually don't recall what we fall back to. I can't recall if it's a pure round robin, a pure random selection at that point. But I do know we favor placing where RAM is more plentiful.
Like on the plan side, is the plan, does the name node tell the plan that what means there's only one particular cache put the jobs over there instead of like you might still be able to cache one particular
Are you asking about like what happens at Mapreduce job submission time in terms of finding? I see. Thank you. So the question is, how does Mapreduce decide task placement, where to run tasks with consideration of caching? The answer is it currently doesn't. So the work is not done of changing the Mapreduce scheduler to inspect the new caching bit on the block locations. The APIs are in place in Hdfs to enable that, but the work hasn't been done on the Mapreduce side yet. And that actually will be very interesting to see what, if any, benefit a map task input sees from this, because this is, in some ways, that's not the ideal use case targeted for this. This was intended more for repeated use. The thing that kept coming up was Hive dimension table. So something that is more side data to the Mapreduce job. I think we're out of time, but if anyone wants to talk further, please feel free to approach me. Thanks again.